Physics requires extreme precision to describe the universe, from the behavior of subatomic particles to the movement of cosmic scale structures. To communicate these measurements accurately, scientists rely on the International System of Units, or SI. This system provides the standardized language that ensures measurements made anywhere in the universe can be universally understood and verified. Scientific collaboration requires a common language. Without universal standards, meaningful data sharing becomes impossible. Consider two laboratories measuring an object. If they use different internal definitions for a single unit, their results will never reconcile. Standardization transforms science into a global endeavor, ensuring that a measurement taken in any laboratory is identical and reproducible anywhere in the world. By relying on universal physical constants, we ensure the integrity of data across time and space. A physical quantity is defined by how it is determined, either through direct measurement or by calculating it from other measurable quantities. Length is an example of an operational quantity. We define it by the process of using a ruler. Speed, conversely, is derived. It is defined by the mathematical relationship between the distance traveled and the elapsed time. The International System of Units is built on 7 fundamental physical quantities. These base units serve as the primary building blocks for all measurements in the physical sciences. Derived units are created by algebraically combining base units. For example, velocity is defined as length divided by time. More complex concepts like force are derived by combining mass, length, and time squared. By relying on this structured hierarchy, scientists can precisely define any physical phenomenon, ensuring that measurements are consistent and reproducible across the globe. The International System of Units, or SI, is built upon 7 fundamental physical quantities that serve as the foundation for all scientific measurement. These base units include length in meters, mass in kilograms, and time measured in seconds. Each unit is defined by immutable physical constants. Additionally, we measure electric current in amperes, thermodynamic temperature in Kelvin, and the amount of substance in moles. Finally, luminous intensity is quantified in candela. Together, these 7 base units create a consistent and coherent framework for scientific quantification worldwide. The second is the fundamental SI base unit of time. While once tied to the rotation of the Earth, it is now defined with extraordinary precision using atomic physics. Specifically, 1 second is defined as the duration of exactly 9,192,631,770 oscillations of radiation corresponding to the hyperfine transition of the ground state of the cesium-133 atom. This atomic-level precision is essential for modern infrastructure. Technologies like GPS rely on these measurements to calculate distance and position with an accuracy that would be impossible without atomic clocks. By basing the second on universal physical constants rather than mechanical artifacts, scientists ensure that a measurement made today is perfectly reproducible anywhere in the universe. The meter, our standard unit of length, is defined by one of the most fundamental constants of nature: the speed of light in a vacuum. It is precisely the distance that light travels in a vacuum during exactly 1 divided by 299,792,458 seconds. By basing the meter on this constant, we ensure that the unit remains invariant, regardless of where or when the measurement is performed. It is a universal constant tied to the structure of the universe itself. The definition of mass has undergone a revolutionary shift. Historically, the kilogram was defined by a single physical platinum-iridium cylinder stored in France. Physical artifacts are susceptible to change over time. which compromises measurement precision. Therefore, as of 2019, the scientific community redefined the kilogram based on the Planck constant, a fundamental property of the universe. This is achieved using a Kibble balance. By precisely measuring the electrical current and voltage required to counteract the weight of a mass, scientists link mass directly to the Planck constant. This constant-based definition ensures that our standard for mass remains immutable, providing the same level of accuracy anywhere in the universe, regardless of time or location. Historically, scientific units were defined by physical artifacts. However, these objects are prone to degradation, damage, and minute changes over time, which compromises measurement precision. By anchoring our measurements to immutable physical constants, such as the speed of light or the Planck constant, we derive units from the fundamental architecture of the universe. This transition ensures that our measurement systems remain perfectly accurate and consistent for eternity, regardless of where or when they are implemented. Metric prefixes allow us to represent vast ranges of values using factors of 10. These prefixes simplify scientific notation and communication across all scales of the universe. By attaching these prefixes to base units, we can express measurements spanning from the diameter of an atom to the vast distance between galaxies. From the scale of nanometers for atomic structures to petameters for space, metric prefixes provide the modular framework necessary for precise scientific measurement. Metric prefixes provide a consistent way to handle scales in science using powers of 10. This decimal system removes the need for arbitrary, non-standardized conversion factors. Consider these examples. The prefix kilo represents a scaling factor of 10 to the power of 3, or 1,000. Conversely, the prefix milli represents 10 to the power of -3, or 1/1000th. This system provides an elegant, scalable structure. By simply shifting the decimal point according to the exponent, you can easily convert between different scales of measurement without complex calculations. Choosing the appropriate metric prefix is essential for transforming complex scientific data into a readable and manageable format. Consider measuring the wavelength of light. Using base meters requires cumbersome scientific notation. Applying the nano prefix simplifies this to an intuitive 500 nanometers. Scientists select prefixes based on the scale of their observation. Nanometers are standard for optics, millimeters for engineering design, and kilometers for geographic distance. The underlying principle is to maintain numeric values within a convenient range, typically between 0.1 and 1,000, ensuring clarity and minimizing errors. The primary advantage of the metric system lies in its decimal structure, which drastically simplifies unit conversions. In the metric system, converting between units only requires shifting the decimal point. Conversely, the imperial system requires cumbersome conversion factors. Consider measuring 1 meter. Converting to centimeters is as simple as multiplying by 100. This consistency across all physical quantities makes the metric system an indispensable tool for global scientific and engineering standards. While the International System of Units provides the global standard for measurement, certain non-SI units remain widely accepted for their practical convenience in daily scientific practice. These units are always clearly defined in terms of their SI equivalents to maintain absolute scientific rigor. The Celsius degree Celsius is commonly used, and its relation to the SI unit Kelvin K is defined as T minus 73.15. The liter L is commonly used, and its relation to the SI unit cubic meter is defined as 1.01 milliquarter. The minute min is commonly used, and its relation to the SI unit second, S, is defined as 1 min equals 60 S. The electron volt EV is commonly used, and its relation to the SI unit joule J is defined as 1 e to 1.602 times 10 manostrine J. By anchoring these units to the SI framework, scientists ensure that data remains consistent and reproducible across all fields of study. The National Institute of Standards and Technology, or NIST, serves as the primary authority in the maintenance of physical reference constants. NIST documentation provides the gold standard for defining these units. By establishing and verifying these constants, they ensure that scientific and industrial measurements remain consistent across the globe. Ultimately, This synchronization is what allows international research to remain collaborative, precise, and reproducible, forming the bedrock of modern metrology. Through constant verification, NIST keeps the world's measurements in perfect harmony. Metrology is the rigorous science of measurement. It serves as the foundation for modern civilization, ensuring that every observation and technical design can be quantified and replicated with absolute confidence. High-precision instruments, such as atomic fountains, exemplify this evolution. They measure the vibrations of atoms to maintain time with such incredible accuracy that a microsecond error could destabilize global infrastructure like telecommunications and GPS navigation. By shifting from physical artifacts to immutable physical constants, metrology provides the ultimate standard for a technologically advanced society. Global positioning systems demonstrate the necessity of standardized units. GPS satellites rely on atomic clocks defining the second to calculate position. The accuracy of GPS is staggering. Because light travels at nearly 300 million meters per second, an error of just 1 microsecond in timing results in a location error of 300 meters. Even a minor deviation in time would result in significant location errors, proving that these standards impact our daily lives. Units of measurement are the fundamental language of nature. They allow scientists to quantify the universe with absolute objectivity. The International System of Units, or SI, establishes a universal framework that ensures measurements are consistent across every laboratory on Earth. A critical advancement in modern metrology is the transition from physical artifacts, which can degrade over time, to definitions based on immutable physical constants. By tying units like the kilogram to constants, such as the Planck constant, we ensure that our standards are derived from the very structure of reality. Ultimately, this evolution provides the precision required for everything from daily commerce to the most demanding scientific research.